here is a quick review for exam 3. Now you got to understand that you have to study as much as you can possibly do and then prepare from the review. So if you only study the review, it's not going to be good. So study as much as you can, but focus on the review. These are the questions that are on the exam, or the type of questions that are on the exam. So the first one, from rotational motion, let us talk about an object rolling down an inclined plane. So let's say it's a sphere, or it could be a cylinder that's rolling down an inclined plane. And we need to find its acceleration. So what you see is the free body diagram. You see the forces acting. All right, you see the weight, and then you see the normal reaction. You have friction. So let's go with weight is mg. And then you have the angle is theta. So the weight can be resolved into two components, mg sine theta and mg cosine theta. And then you have the normal reaction. That is the friction. Okay. So when you calculate the torque, you know torque is F dot R. So friction times R, which is the radius of the sphere or cylinder. But torque can also be expressed as I times alpha. So torque can be written in two ways. We also know that the linear acceleration, which we are trying to find, is alpha times r. So that's the relation between linear and angular acceleration. So what we'll do now is we'll substitute. So from there, alpha is of course a divided by r. So we can take that, plug it into the first equation, which is F times R is I alpha. But instead of alpha, we will now put A by R. So that is, let's call it equation number 1. Now let's look at the forces. What are the forces? mg sine theta minus friction. That's the net force on the x-axis. And according to Newton's second law, net force must be equal to mass times acceleration. Okay? So net force on the down the ramp, we're just taking that. That is the x-axis actually. Okay. So from there, a little bit more math. mg sine theta friction. Okay, so we got the formula for friction from equation 1, which we substituted, because we know that if you take this r to the other side, that's going to become r squared. So that's why it's IA by r squared, okay? Right from there. So which we substitute into that, and then you get mg sine theta is equal to, we're taking IA by r squared to the other side, so MA plus IA over r squared. And we can see that acceleration is common, is the common factor. Take it out, so you would have mass plus I by r squared. So we are almost at the last step. So you can now make A the subject, and you got to take this whole thing down. It'll go to the denominator. So mg sine theta by m plus I by r squared. All right, so that is the formula for acceleration of any object rolling down an inclined plane. So on the test, if it is a sphere, then so it's a solid sphere, then we know that the rotational inertia of the solid sphere is 2 by 5 mr squared. So for a solid, if it's a solid sphere, it's 2 by 5 mr squared. But I think I'm doing it for a cylinder. So if it's a cylinder, it's mr squared. So remember, I will depend on the shape of the object. If it's a sphere, it's 2 by 5 mr squared. And if it's a cylinder, it's mr squared. It's the same as that for a disk. So now, assuming it's a cylinder, I is mr squared by 2. So now you can substitute for I here as mr squared by 2, which is what I'm doing. So mass plus mr squared by 2. And then you also have r squared there. So the r squareds get cancelled. And this can be simplified to mg sine theta divided by, can take the mass out as a common factor. And yes, the r squareds are cancelled, so you have 1 plus half. And 1 plus half is 3 by 2, which flips when you write it in the numerator. So it's 2 by 3 g sine theta. Of course, the masses get cancelled. Okay. So just by knowing the angle of the ramp, so if you're given this angle, that's all you need. You don't even need the mass. You don't need the radius. You can calculate that. So this is one question on the exam. So remember that this formula is the same, but when it comes to this, it depends on what it is. If it's a cylinder, it's mr squared by 2. If it's a sphere, a solid sphere, it's 2 by 5 mr squared. Keep that in mind. So that takes us to the second one. Now, in the second one, I want to talk about angular momentum. Angular momentum, L, is the cross product of R and P. It is the cross product of R, the radius vector, and linear momentum. So you have to know how to take the cross product using ijk vectors. Okay, I'm sure you know that. So this can be written again because it's a cross product of R and P. And I told you P is linear momentum. And linear momentum is mass times velocity. So I'm going to substitute for P as mass times velocity. And then, of course, you can take the mass out because mass is a scalar. And you can take R cross V, which is the velocity. So that's how you would do it. So on the exam, if I give you the vector R and I give you the vector, the velocity in terms of ij and k, you must know how to take the cross product of these two. And then after you take the cross product, multiply it with the mass. So that's number 2. Number 3. Conservation of angular momentum. Now, there is a condition for the conservation of angular momentum, and that is there should be no external torque acting. And in such cases, I1 omega 1 is equal to I2 omega 2. Okay, so let's work out a problem. You just assume that there is a disk that is rotating. And the disk is rotating at 5.0 radians per second. That is the angular velocity, which is our omega 1. The radius of the disk is given as 3 meters. And as the disk is rotating, an object, don't worry about its shape, it doesn't matter, an object which has a mass of 20 kilogram is kept carefully on the edge, or it's just placed at the edge of this rotating disk. Now, when it is placed at the edge of the disk, we know that the rotational inertia of the system is going to change. So the angular velocity will change, and we have to calculate the new angular velocity or angular speed. The moment of inertia or the rotational inertia of the disk is given as 70 kilogram meter squared. So in order to work out this problem, we are going to use the conservation of angular momentum. I1 is the first case when you only have the disk. I2 is the second case when you have the disk plus you have that mass placed at the edge. So that's I2. Omega 1 is of course 5.0. Omega 2 is what we're trying to find. So when you substitute, I'm just writing it down. I1 is the rotational inertia of the disk, which is 70 kilogram meter squared. And then you have I2, which is 70 plus mr squared, mass times the radius squared. And because that object is kept at the edge, we know that the distance is 3 meters, exactly the radius of the disk. So we get the new rotational inertia as 250 kilogram meter squared. Omega 1 is given. We can easily calculate omega 2. So I1 omega 1 is equal to I2 omega 2. And if you make omega 2 the subject, which you can, and you calculate, you're going to get what, 350 divided by 250, which comes out to be 1.4 radians per second. Of course, it's going to slow down. When the rotational inertia increases, it slows down. If the rotational inertia decreases, it will speed up. Just saying. All right, so that's number 3, was it? So let's move to number 4. So here you have something like a beam, a uniform beam, which has, okay, so this is 1 meter long. So it could be a meter stick, okay? It is a meter stick, which is also a beam. Now, since it's uniform, its center of gravity will be exactly at 50 centimeter, and that is the point at which the mass of the meter stick is acting. So you do not know the mass of the meter stick, and you're going to find this. Remember, this is something that you did in the static equilibrium lab. Okay, after you found the center of gravity, you moved it, you moved the pivot to some other point. In this case, it's supported at 30 centimeter, and now we're trying to balance it, so surely you need some mass here. So the mass is 60 grams, and it's exactly at 5 centimeter. Okay, so from this, can you find the mass of the meter stick? Quite simple, quite simple. The condition for equilibrium, there are 2, but we only need the second one, which is the net torque must be 0. So this mass is trying to turn it clockwise, and this 60 grams trying to turn it counterclockwise. And the torques must be equal. How do you calculate the torque? It's this. Technically it's force, but we can use mass here. So the unknown mass times this distance should be equal to 60 times this distance. That's all. Okay, so let's write that. So the unknown mass times 50 minus 30 should be equal to 60 times 30 minus 5. So when you do that, of course 50 minus 30 is 20, and then on the right side you get 60 times 25. Do the math, you will get the mass of the meter stick as 75 gram. It's as simple as that. Just got to remember that in static equilibrium, the total clockwise torque must be equal to the total counterclockwise torque. Let's go to the next. All right, here is the popular ladder question. So there is a ladder excuse me, that is leaning against a smooth wall. So when I say a smooth wall, there's no friction here. So the length of the ladder, the mass of the ladder, and then it's going to be a person who's climbing the ladder whose mass and position will be given. So you have two masses here. One is the mass of the ladder, and since if the ladder is uniform, its mass should act right through the center. And then if there's a person somewhere, that's the second mass. Okay. And then what are these? This is the normal reaction at the ground, and this is the normal reaction at the wall. And there's no friction here because it's a smooth wall, but there is friction here. Okay. So that's the next force. That's the friction. Now you see the mass or the weight actually acting, weight of the ladder. And then there is, let's say the weight of the ladder, the mass of the ladder is 70 kilogram. It's N1, that's N2. Let's call this F. And, okay, the mass of the ladder, so the mass of the ladder is 20 kilogram. And the length of the ladder is 4, 8. So I'm going to change that to 5 meters for easy calculations later. Yeah. So the mass of the ladder is 20. So this is the person, 70 kilogram person standing right there. And you have to find the friction at the ground. That's the question. But again, I'm going to change this to 5 meters because I'm going to say that this is 5 meters, and if I give this to you as 3 meters, then you know this must be 4. I know it's not drawn to scale, but you understand. Because 3 squared plus 4 squared should give you 5 squared, okay? So I give you this, I give you this, you must know how much this is. All right. So the first condition for equilibrium is that the total up force must be equal to the total down force. So we're talking about the y-axis, and there's only one up along the y-axis, and there are two down along the y-axis. So that's why N1 should be equal to 90 kilogram. Clear? We also know that N2, because now if you look at the forces on the x-axis, we know N2 should be exactly equal to friction. We'll come to that. I've not written that. But, so once we have N1, now we're going to apply the second condition, which is calculate the torque. And we're going to calculate the torque about this point. Do you know why we take it at that point? Because automatically the torque due to N1 and F both will become 0. Because there's no distance from that point. They're acting right there. But then that will only leave us two clockwise torques, 70 and 20. Both are trying to turn it clockwise, while N2 is trying to turn it counterclockwise. That is the idea. So 90 times 9.8. I just wanted N1 in newtons, so that's what I did right now. Okay, N1, 90 kilograms, 882 newtons. Okay. So now I'm trying to give you the distances. So BC is taken as 3 meters. All right. And that's when I thought, okay, let me change the length of the ladder to 5. So it makes it easier. So do you understand why AD is 2.0 meter? Yes, because this is going to be 2.5, right? Exactly the center. So D should be the center of A and C. So half of 4, that's why it's 2. All right. And AF is given as 3 meter. So that is given. The person is 3 meters up the ladder. Hold on. So how do we know that AE is 2.4? How do we know? It's just a case of ratio, my dear, ratio. Because AF, if it is 3, then you know 3 divided by, what's the ratio there? How do you get 2.4? Any idea? 3 divided by this big triangle. This is 5, right? So 3 divided by 5 should be equal to AE divided by AC. And we know AC is 4. So I just did that in my head. So 3 divided by 4 should be equal to AE divided by, 3 divided by 5 should be equal to 3 AE divided by 4. I think I should write that. I'm going to confuse a lot of people. Okay. AF over AB should be equal to AE over AC. So, because we have two similar triangles, and that's why AF is given us 3, we know AB is 5, and so we got to find AE, and AC is what? AC is 4. So when you do that calculation, you're going to get 2.4 meter for AE. Okay? So now we can easily calculate the torque, and we're going to calculate the torque about which point? About A. There are two clockwise torques. This is one, this is the second, and here is the counterclockwise. So the clockwise torque is 20 times 9.8, because we need to find the force due to 20, times this distance is 2, plus, now for this one it's 70 times 9.8 times AE, which we determined was 2.4, right? So those are the two clockwise torques added up, and then that should be equal to N2 times this distance. Why are we taking this distance? Stop. We're taking this distance because we always take the perpendicular distance between the line of action of the force and the point, which is this. See? This is the same as this. So it's always the perpendicular distance we take. So that's why it's N2 times 3. And now it's a math. And do the math and you will get the answer as 222.1 Newton. And since we know that friction should be exactly equal to N2, that is the value of friction. 222.1 Newton. So look at this problem carefully. This is a good one and it's on the exam. A ladder leaning against a smooth wall. And now you know. All right, here is the next. Again, I'm going to talk about torque here. So if you have a door, so that's a door, the hinges are here, and the door knob is here. The easiest way to apply a force to open the door is to apply the force perpendicular to the door. Now, that means the angle is 90 degrees. Right, with the door. Sine 90 is 1, you get maximum torque. On the other hand, if you apply a force at another angle, let's say 30 degrees, you're not going to get that same torque. You will get less. So let's calculate the torque in both of these cases. So let's assume that the force applied is 6 Newton in each case, and we'll calculate the torque. So those are the hinges, and let's take this distance as 1 meter. That's the width of the door. And this is, we call it F1, this is F2. First, let's calculate the torque due to F1. So the formula for torque is RF sine theta. But remember, oh, that's a mistake. It's not sine 30, it should be sine 60. Tell me why. Because the angle has to be taken with the door. So if this is 30, this is 60. So keep that in mind. And that's a mistake. I'm going to correct it. I'm glad I caught it. Okay, now, all right, whenever I catch it. But when it comes to torque 2, it's easy because it's RF2 sine 90 in this case. Oh, that's when I caught it. So I'm going to go back and change it to 60. So that changes to a smaller torque. So that becomes, actually it becomes bigger than sine 30. Okay. 5.2 Newton meter. But for the second force, the torque is 1 times 6 times sine 90 is 1. So it's just 6 Newton meters. So you see there, a bigger torque, in fact, the biggest torque with a force is when you apply it at right angles to the door. Remember that. Okay. And also do not make the same mistake that I made. You always take the angle with the door. So if I give you this angle, do not use that. Use 90 minus whatever angle I give you. All right, now you know. Let's go to the next one. So here is simple harmonic oscillation. You know, there are equations for displacement, velocity, and acceleration. Please learn all that. But in this question, you are given the equation for displacement. And you have to calculate the velocity at a certain time. So let's say t is 0.8 seconds. That's what you have to calculate. So once you're given the equation for displacement, you know how to get the velocity. Velocity is dx by dt, so you have to use a little calculus. So you got to take the derivative of that, which is 10 centimeter. So I'm going to keep it in centimeters. But you know, when you do cosine, you get negative sign. So that's why you have the negative there. And then sine, I substituted the value of t, but also you got to multiply with omega. So that's why you see that there. Because when you do cosine omega t, you get negative sine omega t times omega. All right, so because omega is a constant. And you also have to remember that this is in radians, this whole angle. So put your calculator in radians, multiply these two first, and then find sine of that angle when it's in radians. I did that, and I got negative 10.65 meter per second. Do remember that that angle should be in radians. So if I had asked you to find the acceleration, quite simple. You'll have to do the calculus again, because you know that if you do this, you're going to get acceleration as dv by dt, and then substitute likewise the value of time and you will get it. Okay. Now you know that too. So moving on, I just want to give you two formulas in harmonic oscillation. Remember that for a simple pendulum, the time period is 2 pi square root L by G. Time period does not depend on the mass of the pendulum. On the other hand, if it's a spring, light spring with a mass, now the time period does not depend on the length of the spring. It only depends on the mass and the spring constant. So there are two questions based just on that, and be careful. So it's just algebra. If I give you the time period and I give you the length, you should be able to find out the acceleration due to gravity of a particular planet, assuming that this pendulum is on another hypothetical planet, okay? So be careful, understand all the terms. Again, length has to be in meters, and you will get g in meter per second squared. In this equation, m has to be in kilograms, and k is the spring constant in Newton per meter. All right, so that will take us to the last one in this short review. So let's say you have a beam 5 meter long and it's uniform, so that's the weight of the beam right through its centers, 100 Newton. And let's say it's supported at two supports. So you got one support here, which is 1 meter from that end. and you got the other support right at the other end. Okay. And the question is, can you find the normal reactions at the two supports? So there's an object kept here. The object has a weight of 150 Newton. So you have that, and that is 4 meters from that end. Okay. So you have two normal reactions, N1 and N2, and the idea is to find that. Okay. What are the two conditions? Number one, the total force up should be equal to the total force down. That's what you see there. The total force up is N1 plus N2. Total force down, add these two. That's so simple. Next condition is the net torque must be 0. And that means the total clockwise should be equal to the total counterclockwise. And I'm going to calculate the torque at the left end, which means all distances have to be measured from the left end. Okay, so what are the clockwise torques? Can you tell me? Well, you can't talk to me, so okay, anyway. So this is clockwise, this is also going to be clockwise. N1 and N2 are going to be counterclockwise. I think I'm going to draw that. So taking the torque at the left end. So that's clockwise 1, clockwise 2, counterclockwise 1, counterclockwise 2. Easy. So 100 Newton times this distance, which is 2.5, plus 150 times 4, because it's given as 4 meters, should be equal to N1 times 1, because the distance is 1, plus N2 times 5. But instead of putting it as N2, I just put it as 250 minus N1. Is that right? Yes, it is. Because if you make N2 the subject here, you're going to take this to this other side, and you will get N2 is 250 minus N1. Agreed? That's why I put it here. In place of N2, I have 250 minus N1. So now the only unknown quantity is N1. Just do the math. N1 times 1 is N1. And then this you have to distribute. So that's what I've done. And then, oh no. N1 minus 5 N1 is not 6 N1. Okay. So on the left side, 250 plus 600. And this is minus 4 N1. Yeah. And I'm taking that to the left side, becomes positive, and then when I do the math, taking these two, that's 850. So 1,250 minus 850 is 400, and you can check it out in your calculator. N1 is 400 by 4, which is 100 Newton. So if I get N1, I can find N2, because I know N2 is what? 250 minus N1. That gives you 150 Newton. That's it. Remember that this review is not everything, but should be the focus. You have to absolutely listen to everything I said in this review, really digest it, understand it, learn how to work out these problems, and you're going to do very good in exam 3. But do also work out more problems. Wish you all the best. Thank you.